So we define row space here, the space generated by rows of the matrix, that's what we call the row space. And similarly, the space generated by columns of the matrix is called a column space. And of course, we discussed about the dimension of the row space and the dimension of the column space. And we could see column space is going to be subset of what, and similarly row space is going to be subset of what, that we have seen. Suppose if you have an m by n matrix, let's say A is a matrix of size m by n. When you look at the row space of A, so that is going to be a subset of Rn. Why? Because if you see that in a row there will be n elements because there are n columns. And similarly, if you look at the column space of A, so the column space of A, that's going to be subset of Rm when you take a matrix of size m by n. And today let us discuss more about it. So let's start with the matrix. Let A equal to 1, 1, 2, 3, 1, minus 1. And let me take 1, 0 here. Then this one is 5 and it is 3, whereas it is 3 and this is 2. So now the question is, find basis of row space of A. So you need to find the basis of row space of A. So now you can simply do one thing. We know how to reduce a matrix to echelon form, a row reduced echelon form. So once if you reduce the matrix to reduced echelon form, then it is easy to identify what are the basis of the row space. So you know elementary row operations, right? Elementary row operations. It means multiplying a row with constant and adding two rows. For example, if you take this matrix, so now A, what I'm going to do is I'm going to change the second row to this second row minus the first row, or the second row minus the 3 times the first row. Then you're going to get a matrix. That's what 1, 2, 1. So when you do that, you get 0 here, R2 minus 3 R1. I get minus 2 here, and then minus 6, so minus 7 here, minus 3 here, and 5, 3, 3, 2. Right? So here I made a row operation here. It means the second row I replaced with the second row minus the 3 times the first row. So when you do these row operations, the row space remains the same. There will be no change in the row space when you do some row operations. Okay, why? Because you are taking the given vectors, like let me assume this is the first row and the second row, the third row, right? So you are given with these 3 rows. Now what you are doing to this second row, you are going to replace it with R2 minus 3R1. So even if you do that, there will be no change in the row space. The space generated by R1, R2, R3 will be same as the space generated by R1, R2 minus 3R1 and R3. Okay, so elementary row operations will not change the row space. So you can write a theorem. The theorem says that, so let me mention the theorem here. Elementary row operations not change the row space. Okay, so the row space is going to be same. Now to find basis of the row space, we'll do one thing. We'll apply some elementary row operations and we'll remove the dependent rows if there are any. Removing dependent rows, we mean if there is a dependent row, when you convert the matrix to echelon form, that row will become 0. For example, when you look at this matrix, I have written this third row like this. 2 times of R1 plus the second row. That is what I did. That is how I have written the third row here. 2 times the first row plus the second row. If I do that, I think this is 2 plus 1, fine. Okay, that is 4 minus 1, 3, correct? 2, yeah, that's correct. Okay, so when you do row operations, what happens is this third row will become 0. Let's see how. So now I'll take A. So you know what is a reduced echelon form, right? So if you have a matrix A, right? So the condition is the first non-zero element in each row must be 1. So let's say example 1, 0, 0, let's say 5, 0, 1, 0, let me take 2 here and 0 here, 0 1 0 1 0 0, and here 0 0 0 1. So if you look at it, this is the reduced echelon form of a matrix. Like it's not a reduced echelon form of A, this is some reduced echelon form. And the main condition what we need is the first non-zero element must be 1. So if you look at the first row, the first non-zero element is 1. In the second row, the first non-zero element is here, it is 1. In the third row, the first non-zero element is here. So the first non-zero element must be 1. For example, if you have 2 0 0 1, this cannot be a row reduced echelon form. Why? Because if you look at the first element is 2 here. The first non-zero element in the first row, it is 2 here, so this cannot be reduced echelon form. But if you divide the first row with 1, yes, it will be reduced echelon form. So that is the one condition. And the next one is this first non-zero entry, we call it as a leading coefficient. So the leading coefficient must be 1, or we may call it as pivot. It has another name as well, pivot. Pivot must be 1. And if a column contains pivot, let's say this column contains pivot. Now, except that element, the rest of the element must be 0. You see the first column and as well as the second column and the third column. These column contains pivot elements, and except that elements, the rest of the elements are 0 in that column. Suppose if I take this matrix, another matrix like 1 0 0 0 1 0 2 0 1. So here when you look at this matrix, the first non-zero entries are 1 only, there is no issue. Now you look at the first column, there is no problem, and second column no problem, and the third column, it contains pivot element, but I am able to find a non-zero entry other than this. So now this cannot be a reduced echelon form. So that is the second condition. If a column contains pivot element, then the rest of the elements must become 0 in that column. And the next thing is, these pivots must be adjusted in this order only. For example, if you look at the pivot position of the second row, that must be right side to the first row. What I mean, if you have a matrix like this 0 1 0 0 0 0 0 1 1 0 0 0, so the pivot elements are 1, and here it is 1, and here it is 1. But if you look at the order, for the first row, the pivot element is at the second position, and for the third row, it is at the fourth position, whereas for the third row, it is at the first position. But when you look at this order, it should go in an increasing order, like first you get 2, next you get 4, next you get 1. No, this is not allowed. But if you write this 1 here, then this will be fine. It means you should make some row operation, like what you have to do is you take the first row to here, you interchange these two rows, then one more time you interchange these two rows, then you will get this form 1 0 0 0, and then 0 1 0 0 0 0 0 1. Now this is a reduced echelon form. Okay, so these are the three conditions you need to keep it in mind to check whether the given matrix is in the reduced echelon form or not. First non-zero entry in each row must be 1. Then if a column contains pivot element, then the rest of the elements are 0 in that column, and the pivot element must be arranged in an increasing order. And if there are any 0 rows, and this is also one more thing, if there are any 0 rows, you must keep it at the bottom of the matrix. So if a matrix satisfies all these 4 properties, I say that matrix is in the reduced echelon form. Now let's do one thing. Let's try to convert this matrix to a reduced echelon form. Then let's find what is the basis of the row space of A. Why? Because when you make row operations, the row space remains same. So let me start doing row operations here. So you take A, so you try to replace R2 with R2 minus 3R1. See, this is the first non-zero element in the first row. So except this, I have to make the remaining 2 as zeros. So to get a 0 here, I'll replace the second row with R2 minus 3R1. Similarly, the third row can be replaced with R5, R3 minus 5R1. So when I do that, 1, 1, 2, 1, and this is 0, 1 minus 3 minus 2, and minus 1 minus 2, sorry, minus 6, so minus 7, and this is minus 3. And this guy, 1 minus 5 minus 5 will be 0, 3 minus 5 minus 2, and 3 minus 10, that's minus 7, and 2 minus 5 minus 3. You can see that the second row and the third row are almost same. Now let me make one more row operation, that is R3 is replaced with R3 minus R2. So 1, 1, 2, 1, and 0, minus 2, minus 7, minus 3. So when you subtract it, you get 0, 0, 0. You see, the third row depends on the first two rows. So that is why you can see that you get 0 in place of third row. And of course, once if you write the first row, so third row as a combination of the first two rows, then definitely the first row also expressed as a combination of second and third rows. But anyway, if there is a dependent row, in that place you are going to get 0 here. Okay, so but is it in the reduced echelon form? The first non-zero element here is 1, there is no issue. In the second row, the first non-zero element is minus 2, but this I have to make it 1. So to make it 1, so I'll divide the second row with minus 2. So I get 1, 1, 2, 1. Okay, 0, 1, 7 by 2, whereas this is 3 by 2, 0, 0, 0, 0. Okay, so the first non-zero element in the second row is 1. But when you take this column, except this element, the rest of the elements must become 0. So let me make this element as 0. So to make it, I am going to replace R1 with R1 minus R2. So when I do that, so we started with A and we reduced the matrix into reduced echelon form, and we can find the non-zero rows here. So non-zero rows, you can take it as the basis of the row space of A, or in other words, you can take the corresponding rows of A as a basis of row space of A. Okay. Now the question is about column space. So how to find the basis of a column space? So when you make row operations, what happens to the column space? Is it going to be changed or remains the same? So let's try to see. Let's say here A I have given. So what is the row space of A? Can you see that? The row space of A is nothing but linear combination of these two rows. If you observe that the first row is 1, 1 and the second row is 2 times of 1, 1. So now you can see that this is the space generated by 1, 1 itself, where alpha belongs to R. Okay, or in other words, you can simply write it like this: alpha, alpha, where alpha belongs to R. So this is the row space of A. But when you let me do one thing. Okay, let me look at the column space of A. Now the column, and if you observe that the two columns are same. 1, 2, 1, 2. The first column is 1, 2. The second column is 1, 2. So the column space generated by this vector 1, 2 is all multiples of that 1, 2 itself. So the column space generated by this is just alpha times, or let me take some beta times 1, 2, where beta belongs to R. So if you look at any element in the column space, it always looks like beta and 2 times of beta. That's it. Now let me do one thing. Let me apply some row operations to A. So what I'll do is I'll apply row operations to A. So that is 1, 2, 1, 2. Now let me replace the second row with R2 minus 2R1. R2 minus 2R1. So when I do that, I get 1, 1 and R2 will be replaced with 0, 0. Because 2 minus 2, 2 minus 2 will get 0. Now, of course, you can see this is the reduced echelon form of A. Okay, this is the reduced echelon form of A. Do you agree? Is this a reduced echelon form? Let's see whether it satisfied all conditions or not. The pivot element is 1 and this column contains pivot, so the rest of the elements are 0. So the second condition is done. and in the second row, first non-zero element, there is no non-zero element in the second row, so no worries. That's it. It is in the reduced echelon form. Okay. Now let me look at the column space of this new matrix. Let me suppose this is A, and this one is A prime, or EA, not A prime. Let me write it as echelon form of A. So if you look at the column space of A, you can see it is all multiples of 1, 2. Whereas the column space of EA, so that is all multiples of 1, 0. That is, let's say some x into 1, 0, where x belongs to R. You can see that these two spaces are not same. So let me represent the column space with this notation: column space of A, and this is the column space of EA. Okay, you can clearly see that these two are not generating the same space, but it may be generating a same dimensional space, but it is not generating the same spaces. Okay, I can clearly see that here the column space of A is not equal to the column space of EA. Okay, so now when you make row operations, I mean elementary row operations, the column space may change, but when it comes to the row space, it remains the same. But now the question is, sir, how to find basis of a column space? If the column space is changing, can I find the basis of a column space with the help of the reduced echelon form? Answer to this question is yes, you can find. So what you can do is, after reducing the matrix into reduced echelon form, you try to identify the columns which contains pivot elements. What are the columns which contains pivot elements here? Only the first column contains the pivot element. So when it comes to the basis of a row space of column space of A, you can say that, let me write, basis of column space of A, that's equal to just the first column. Here if you observe that the space is changing but the dimension remains the same. And okay, we need to discuss few properties related to row equivalent matrices. Do you know what is row equivalent matrices? A and B are said to be row equivalent when B can be obtained by making some elementary row operations on A. For example, you see this A and EA are going to be row equivalent. Why? Because just by doing some row operations on A, I'm getting EA. And for example, let's say A equal to 1, 1, 1, 3, 1, 2, and then let me simply add 4, 2, 3. So this is A, and let me take B. So where B is 4, 2, 3, 3, 1, 2, 4, 2, 3. So if you observe that this A and B are row equivalent. Why? Because I can see that A can be obtained by making some row operations, B can be obtained by making some row operations to A. For example, B can be expressed as E times A. You may ask me, what is this E? E is nothing but what is the operation I did? What I did is I replaced the first row with R1 plus R2. So 1, 1, 0, 0, 1, 0, 0, 0, 1. B can be expressed as E times A, where E is an elementary matrix. This is the elementary matrix I am taking. See here, if you observe that when you multiply E with A, 3, 1, 2 and 4, 2, 3, you see that the third row is 0, 0, 1. So after multiplication, the third row remains the same because 0 times first row plus 0 times second row plus 1 times the third row. So I'll get the third row as it is. There is no change. And similarly, you look at the second row. The second row is 0, 1, 0. So when you multiply with it, in place of second row, you'll get the second row of A only. Why? Because 0 times first row plus 1 times second row plus 0 times third row. So I get 3, 1, 2. But when it comes to the first row, what happens? The first row and the second row will be added. So 1 times this plus 1 times the second row plus 0 times the third row. So I'll exactly get 4, 2, 3. Okay, so row operations can be denoted with this elementary matrices. So after making some row operations, I'm able to find B from A. So therefore, we say that A and B are row equivalent. Okay, so there is a theorem about row equivalent matrices. So let me just show you. Yeah, so here is a theorem which talks about row equivalent matrices. If A and B are row equivalent matrices, then given a set of column vectors of A is linearly independent if and only if the corresponding column vectors of B are linearly independent. It means when you know A and B are row equivalent, so let me represent C1, C2, C3 and so on Cn. These are the columns of A. And similarly C1 prime, C2 prime and so on Cn prime. These are the columns of A, columns of B. And I know A and B are row equivalent. Suppose if you know that like C1, C3, Cn, these are linearly independent, then definitely the corresponding columns here must be linearly independent if they are row equivalent. So that is what this statement says. And the second statement says, if a given set of column vectors of A forms a basis for the column space of A, if and only if the corresponding column vectors of B forms a basis for the column space of B. So I came to know that the first column, second column and the last column. Similarly, the first, second column and third column gives the basis of column space of A. Then definitely if A and B are row equivalent, then first, second and the nth column should give me the basis of column space of B. But remember one thing, the column space of A may be different from the column space of B. We are not saying that those two are equal. But even though they are not equal, what I can say is, if the first two columns forms a basis of A here, then definitely the first two columns in B forms a basis of column space of B. That's what it says. Okay. So with the help of this statement, I can tell you what is the column space of, what is the basis of column space of A for the first problem. For example, here is A, right? So I know what is its reduced echelon form. This is the reduced echelon form. And we know one more information. The information is reduced echelon form and A both are row equivalent. So since these two are row equivalent, now what are the basis for the column space of A? If you ask me what is the basis for the column space of A, I simply say the columns which contains pivot elements. So the first column and similarly the second column. These two columns contains pivot elements. So these two are going to be basis of column space of this matrix. You can easily see with the help of 1, 0 and 0, 1, you can actually create all these things. Minus 3 by 2, 7 by 2 can be expressed as a linear combination of first and second column. Minus 3 by 2 times the first column plus 7 by 2 times the second column will give me this third column. Similarly, fourth column can be obtained with the help of first and second. So definitely you can see that first and second columns are basis of column space of B. So now what are the column space of what are the basis of column space of A now? That's going to be first column and the second column of A. So now if you ask me this question, what are the basis of column space of A? I'll simply write here basis of column space of A. Let me write it like that equal to, so the first column of A, that is 1, 3, 5, and the second column of A, so that is 1, 1, 3. So this is the basis of column space of A. Is it clear now? So once if you know the reduced echelon form of A, we can tell what are the basis of row space of A and similarly what are the basis of column space of A. Okay, now let us look at one more example. So here is a problem. Find basis for the row and column space of A. So what is the idea? You reduce it to echelon form and the corresponding non-zero rows, you can say the basis of row space of A. Now you look at the columns which contains pivot elements. Now you take the corresponding columns of A and you say they are the basis of column space of B. Right. So now let us see what is the reduced echelon form of A. Now this is the reduced echelon form of A. Right. Now you see what are the non-zero rows? Non-zero rows in R. The first rows, the second row, and the third row. So you can write this first, second, third rows as the basis of row space of A. But when it comes to the column space, I need to look at the columns which contains pivot element. So the first element here, this is the pivot element, and the first non-zero element here is this is not actually reduced echelon form, it is just an echelon form. The difference between the reduced echelon and echelon form is, in the echelon form, if you have a pivot element, the below elements will be 0. We do not worry about the above elements. But whereas in the reduced echelon form, we take care of all elements in that column. So we'll make this as 0. Okay. But okay, fine. So if you have reduced echelon form or echelon form, anything is enough to find basis of row space and column space. Okay. So this is one pivot element. Next here is one. The first non-zero element is here. So this is the first column, and this is the third column, and this is the fifth column. Therefore, the basis of column space of A. So the basis of column space of A, these are the first column of A, that is 1, 2, 2, minus 1, and next comma, the second third column, so that is 4, 9, 9, minus 4. Now the fifth column, so that is 5, 8, 9, minus 5. Okay, so this is the basis of column space of A. Now similarly, let us write what is the basis of row space of A. I may write it like this, row space of A. So you see the first and second and third row of the echelon form. That's what they have written. So you can say the basis of the row space of A are nothing but R1, R2 and R3. So where R1, R2, R3 are given here. Or simply you can do one thing. You can take the corresponding rows of A as well. Okay. So this is about a row space and the column space. Now let us discuss about the null space. I hope you are clear how to find the basis of a row space of A and the basis of the column space of A. Okay. Now let us define null space of a matrix. So let A be a matrix of any size. Let me take a rectangular matrix. Let A be an m by m matrix. Okay. So the solution space of Ax equal to 0 is said to be null space of A. Okay. So this is simply the solution space of Ax equal to 0. Where you may ask me, what is this x? X belongs to Rn. Okay, it's a coordinate vector belongs to Rn. That's what I mean. Because it is an m by n matrix, so you should take a column of size n. So simply you can say that this is just a solution space of Ax equal to 0. See, for example, let's take A equal to 1, 1, 1, 0, 1, 2. This is A. The question is to find null space of A. Find the null space of A. We need to find the space. It's not the basis of null space of A. First let us find the null space, then we can talk about its basis. So what do you do? So we'll immediately calculate A times x equal to 0. This is what, right? So that's what 1, 1, 1, 0, 1, 2 multiplied with what must be the size of x. This is a 2 by 3 matrix. So it should be from R3. So let me take it as x1, x2 and x3. And this should give me 0, 0. Right? So now you solve for it. So when you solve it, x1 plus x2 plus x3, that gives me 0, and 0 times x1 plus x2 plus 2x3. This gives me 0. So from this you can tell what is x2. x2 is actually minus 2x3. And if x2 is minus 2x3, from this you can tell what is x1 in terms of x3. So x1 equal to minus x2 minus x3. So minus x2 is nothing but 2x3 minus x3. So this is x3. Therefore x1 is x3, x2 is minus 2x3. So now we can write, therefore the null space of A, we can simply write n of A, the null space of A, which is equal to x1, x2, x3, where x1, x2, x3 are satisfying these equations. So let me write. So x1 must be some t. If I take x3 to be t, so x1 is t and x2 is going to be minus 2t, where t belongs to R. Okay. So this is the null space of A. Now if you ask me what is the basis set for null space of A, it is easy, we can write. So the basis of n of A, that will be, you can see that it is generated by the element 1, minus 2 and 1, because it is t times of 1 minus 2 1, right? So the basis of null space of A is just it contains one element, that is 1 minus 2 1. So if you ask me what is the dimension of null space of A, I'll say that is 1. Why? Because there is only one element in the basis set. So the dimension of null space of A is 1. Okay. But every time this process may not be easy. Why? Because here I directly solve the linear equations and I told you what is the null space of A. But here if I have a big matrix, for example, let's take the first case or this case itself. Now if I add one more question here, the null space of A as well, null space of A. So you need to find the basis for null space of A as well. Then you can do one thing. So this is what you'd like to find, the solution space of Ax equal to 0. And do you remember how do we solve these equations Ax equal to 0? First you'll write the augmented matrix and you'll perform some row operations to it and you'll reduce it to echelon form. Once if you get the reduced echelon form, you'll get a simplified equations and that can be written very easily. Okay, from that we'll get the solution space. That is what we did. Right? So the same process you can do. So here you take that matrix, reduce it to echelon form. So here you can see the reduced echelon form of A. This is the reduced echelon form of A, right? So now I'd like to find the basis of null space of A. So now I'll do one thing. So I'll write the equations here, because this will be 1, 2, 3, 4, 5, 6. There are 6 columns. Therefore, this will be x5 plus 5x6 equal to 0. So from this you can write what is x5. That is minus 5x6. Now from the second row, I can write x3 plus 3x4 minus 2x5 minus 6x6 equal to 0. You already know x5 in terms of x6, so you just replace it here. Now you try to write x3, you try to express x3 as a combination of x4 and x6. Okay, and the next you look at the first row. So from the first row you can write an equation. Now you can express x1 as a combination of x2, let me call cx2, and there will be no x3. Why? Because x3 can be expressed in terms of x4 and x6, and there will be no x5. So ex4 plus dx6. Do you understand? Okay, so this I wrote it from the third row, and this one I wrote it from the first row, whereas this one I wrote it from the first row, and this one is second row. So now you see x1 is expressed in terms of x2, x4, x6, and x5 is expressed in terms of x6, and x3 is expressed in terms of x4 and x6. So when you look at it, how many unknowns are here? So finally x2, x4, x6. That's it. So let me write that space. C into x2 plus E into x4 plus D into x6. This is what you will write in place of x1. Whereas x2 is just x2. And x3, that is ax4 plus bx6. And x4 is x4 only. And x5, that is minus 5x6. And x6 is x6 only. Now you can see how many of them are there, how many unknowns are there. x2, x4, x6. So there are 3. So it is 3 dimensional. So the null space of A is a three-dimensional matrix. Sorry, it's three-dimensional space. To find the dimension, no need of finding the solution space. You can actually get it from here. You know the rank of this matrix is 3. Why? Because in the echelon form there are 3 non-zero rows. So the rank is 3. So if you want the dimension of the null space of A, that is simply number of columns minus rank of the matrix. Number of columns are 6 and the rank of the matrix is 3. Therefore 6 minus 3, it gives me 3. Okay, we'll discuss rank nullity theorem. So there you can see that the dimension of null space of A is going to be number of columns minus rank of A. That is the dimension of null space of A. Okay, and better do one thing. I shared one reading material like that. That is the one you have studied when you are in PUC2, like just after PUC2 and before E1. Okay, so you just go through it so that you can recall basics quickly, because this course is extension of whatever you studied there. It is not that just exactly the repetition of the same. It's exactly the extension of what you have studied there. Okay, either you write reduced echelon form or echelon form, anything is fine to find the basis. And there is one more important thing I'd like to discuss. Here we can conclude one more thing. Like, elementary row operations are not changing the row space. And there is one more theorem that says that the elementary row operations do not change the null space. Okay, so let me present the theorem here. So here is the theorem which states elementary row operations do not change the null space of a matrix. Okay, if two matrices are row equivalent, then you can conclude that their null spaces are same. So there is one more thing. So there is another theorem which states that a linear system of equations that Ax equal to B is consistent if and only if B is in the column space of A. It's very easy to see. For example, I have a matrix A. Right? Let me start with a 2 by 2 matrix A, B, C and D, and you multiply that with x1 and x2. Okay, so what is the resultant? So the resultant will be, you can write it like this, right? x1 times the first column, that is AC, plus x2 times the second column, that is BD. So when you multiply A times X, so you will get a vector which is generated by the columns of A, or which is nothing but a linear combination of columns of A, right? So not only for this, however big matrix you take, let's say I am taking a matrix A where this can be represented as C1, C2, C3 and so on Cn, where C1, C2, C3 are columns of A. Okay, now let me multiply with X, that is A times X, so which is x1, x2 and so on xn. So this equal to, so multiplication is defined this way, right? x1 times the first column plus x2 times the second column plus and so on plus xn times the last column. Now what I observed here is the linear combination of these columns C1, C2 and so on Cn. So now it is clear that A into X is nothing but linear combination of columns of A. So linear combination of columns of A, right? So now if you write Ax equal to B such that B is not in the column space of A, then you cannot say that this solution, I mean this linear system is consistent. When do you say a matrix linear system is consistent? If it has a solution, we say it is consistent. If it doesn't have a solution, we say it is inconsistent. So if you want to find a solution for this Ax equal to B, then definitely B should come from column space of A only. When B can be expressed as linear combination of columns of B, then only I can say that this system is consistent. Then only you can find a solution for this system. Otherwise, no. Okay, so that is what this theorem says. If Ax equal to B is consistent, then definitely B is in the column space of A. It means B can be expressed as a linear combination of columns of A. Suppose if B is in the column space of A, then Ax equal to B is consistent. Okay. Now let's look at a small problem. So determine whether B is in the column space of A. And if so, express B as a linear combination of the column vectors of A. Okay, so let's see how. So what you have to do is you just write you write the augmented matrix. It's like 1 minus 1 1 9 3 1 1 1 1. This is the matrix where 5 1 minus 1. This is the column B. Now you do one thing, you just find the solution of Ax equal to B. This is what you need to do. Okay, so once if you came to know that the solution is x equal to something, okay, let's assume that the solution is A, B, C, then definitely then we can express B as a linear combination of columns of A. So now B can be expressed as, oh, this B and this B may coincide. Let me do one thing, let me tell you what is the solution here directly. So 1 minus 3 1. So this is the solution for the first problem. You can see that 1 you just add first 2 rows and you subtract it from 3 times of the second row. Yes, I get 5 and this gives me 10 minus 9 1, correct? Yeah, it's giving me. So therefore you can see that B equal to 1 times the first column, that is 1 9 1, minus 3 times the second column, minus 1 3 1, plus 1 times the third column, 1 1 1. So that's what exactly B, where B is nothing but this 5 1 minus 3. Okay, I can tell you what is the reduced echelon form of A here. So the reduced echelon form of A, that's going to be 1 0 0 1 0 1 0 minus 3 0 0 1 1. So this is the reduced echelon form of A. Okay, so similarly you solve the next problem. Try to express B as a linear combination of columns of A. So if it is consistent, then it is possible. If it is not consistent, then it is not possible, right? Okay, so I'll stop it here and let me know if you have any questions or doubts.